All right, how's everyone doing? So I did not talk about service learning project yesterday, so let's talk about the service learning project. Let's watch me log in first. So if you were not in 222, 224, if you're kind of hopping into this, then the SLP may not make sense to you, in which case come and talk to me. But assuming that you've been doing the sequence, so this is the third part of your service learning project this quarter. So a couple of things to note. First of all, the presentation is again the last Tuesday of the quarter. Okay, so that's going to be April 12th, sorry, that's going to be June 11th, right, 3 to 5 in the digital lounge as usual. If you cannot attend that and you want an exception from attending, you have to let me know by email by Friday, 5 p.m. Okay, this Friday. Otherwise, I'll expect that you will show up and have a good time at the presentation. So the other thing to note is that for this spring quarter, your final upload for the SLP is not the one-page poster, okay? It's a full-blown technical report on your project. And I've put a link to an outline that lists the sections that I need to see in your report, okay? But your report needs to be a document. Okay, so here's the mindset. In fall, you came up with this idea for an SLP. I'm going to make a dog bowl that controls how much food my dog gets, right? And it's going to have a camera, and it'll take a picture of my dog when it's eating, and it'll send it to my phone. Okay, so you went to a venture capitalist and you said, here's my idea, I would like $1 million. And they said, sure, and they gave you $1 million, right? Okay, this report is what you're going to give to that venture capitalist and say, here you go. Okay, I've done my project, here's my report. So this report should completely describe your project, right? What you were trying to do, what problem you were trying to solve, what approach you took, what your research showed, what other people are doing, the advantages and disadvantages of your approach over other approaches, and so on and so forth, as well as complete details about the solution you came up with. Circuit diagrams, system diagrams, list of components, code, flow charts, pseudocode, everything that somebody would need to be able to reproduce your work. Okay, so somebody who knows nothing about your project, somebody who is not you, can take this report and they can do what you did. They can build your automatic dog bowl food system or your whatever, right? And so there's an outline you can get to on Canvas in that section if you click through that, which is this project report template. And it just sort of lists 7 sections that I would like to see in your report. So title page on the front, right? But then objectives, right? What were you trying to do? What was the problem you were trying to solve? Research analysis, so other solutions, competitive analysis, what are other people doing, pros and cons. Part 3, probably the biggest part, solution specification. That's all the detail about your solution. If you have a lot of code, you're welcome to put your code on Git and then just provide a link in the report, so you don't need 100 pages of C code in your report, but you can do that too. But all the information on how to basically do what you've done. A section on how you tested it, how did you verify whether or not this worked. So what tests did you run? So a test plan and the results of following that test plan. Discussion of next steps. If you were going to continue developing this, what would you do down the road? How would you enhance or improve this or change it? Lessons learned, right? This is a 3/4 of a year project that is not just busy work. Hopefully it's intended to let you learn some new stuff about some other areas outside of your coursework. So what did you learn, right? What did you figure out along the way of this? What's the sort of take home from it? And then the last part is license terms. And you're disclosing in this report everything that there is to know about this project, right? If you do not want that to be made publicly available, tell us. Okay, put in license terms saying something like, you know, this is proprietary information, I'm turning in this report for the sake of getting a grade, but do not publish it, do not disclose it without written permission, or something like that. I can help you with that if you want. If you don't mind having it out there, if you want it to be totally open, you can use license terms such as this. So this basically says anybody can do whatever they want with this, right? So that's the other end of the spectrum. But put some kind of license terms in there so that we know whether we can publish this report on the web or we have to keep it, you know, secret. You know, and Izad or I can help you figure out wording for that if you like. And then this is just basically what I already said. Occasionally people will copy this and they'll write 1 or 2 sentences after each of these things, right? That is not a technical report. Okay, that might be fine for like a page of homework or something, but for a report that'll probably get you close to a 0. So think, you know, standalone document. Okay, more than a lab report. This is hand it to somebody who has never seen your project before, hasn't been doing the work, but they want to be able to build what you built or create what you created. Does that make sense? So that's your final upload. It's a PDF, and that needs to get uploaded by June 3rd. So that's the Monday before the presentations. All right, so any questions on SLP? All right, cool. So I want to run through briefly some comments on the 222 final exam, just to mention some things that I saw that I thought were worth mentioning. And there were 2 copies of this exam, A and B, and they were similar in the kinds of questions they asked, but some of the specifics were different. So if this doesn't look like you know, the exam that you remember doing, that's probably because it's not. But let me just kind of talk through some of this. So question 1 was a recursive. Sorry?
Can you make it larger?
I don't think so. But I can do this. All right. So question 1 was a recursive function. You're either recursively counting the number of nodes in a tree or the number of elements in a list. But the goal was to be using recursion, right? So what's a recursive? Let's count the number of nodes in a linked list recursively. So your linked list is a bunch of things pointing to things with a null on the end. And we know how to do this iteratively. You start here and you just move and follow the pointer to the next node until you're at null, and you just keep a count of it. To do this recursively, right, we rethink how we count things. So how do you tell how many things are in a list? Well, if the list is empty, there's nothing to do. You just say the length is 0. If it's not empty, there's at least a first element. So you grab that first element and you say the list has 1 thing in it. That's this first element. And then you take the rest of the list and you hand that to a friend and say, how many things are in this list? And whatever answer they give you back, you add 1, that's your answer. Okay, that's the essence of recursion. So if the list is null, return 0. Otherwise, return 1 plus count of the rest of the list after the first node. So if the list is null, we're going to say count as 0. Otherwise, we're going to count the rest of the list, add 1 to that. That's what we're going to return. So that's the idea of the recursion. So where do people get into trouble with this? Return the rest of the list after the first node, so count list arrow next. And I'm assuming the usual node structure. Well, this is the tree version, but the usual node structure, you got an integer data or something, and you've got a struct node star next, right? So this represents the list after the first node. This is the number of things in that, right? But if you do this and list happens to be null, you get a seg fault, right? So any time that you're doing recursion, you always want to think about a base case. How are you going to get out of the recursion? And more often than not, you're going to do that check in the very beginning. Because a lot of times that check comes down to, is the thing that I'm being asked to analyze null? And as soon as you do anything with that thing that you're being asked to analyze, if it's null, you're going to seg fault. So I would have this first, and that takes care of both things. It takes care of the base case to get you out of your recursion, and it takes care of the possibility that list is null, in which case this would seg fault. If it's null, I'm not going to do anything else. I'm just going to exit right here. So that was one issue with sometimes seeing, you know, these things in a different order. So if you wanted to actually write code, so if list is null, return 0. Otherwise, count list arrow next. Okay, so here's the second thing that I saw in a few problems. Recursion is not magic, even though I think it is. Calling count on list next is fine. That says I want you to count how many nodes are in the remainder of the list. That's not going to solve your problem for you by itself, right? You can't just hand this list to a friend and say, can you count how many nodes are in here? And your friend says, okay, I'm done. Well, they counted the number of nodes, but does that help you? No, it doesn't help you unless they turn to you and say, I counted the number of nodes is 7. And then you take that and you say, oh, okay, thank you, and you add 1 to that, and you return it. And so in a number of these recursive problems, I saw a lot of cases where people were correctly calling the function recursively, but not doing anything with the return value. Okay, really, really easy thing to forget to do. But it doesn't recurse if you don't do that. So that's one thing to keep an eye out for. All right. So recursive function to traverse a three-way tree. So this tree has 3 children on each node, left, middle, and right. And we want to traverse it with left, middle, right, and then print out the root node data. So LMRN traversal order. And traversal is inherently recursive, right? The way that we do this traversal is first we traverse the left subtree, then we traverse the middle subtree, then the right subtree, and then we print out the root node data. So that is a recursive definition, and it codes pretty directly. So traverse tree. So what's the procedure? Traverse tree left, and so on. Traverse tree mid. Traverse tree right, and then print out the node data. So print tree data. And there's two problems here, of course. One is that this recursion will never end, because I don't have any way to get out of this. And two, if tree is null, these are going to segfault, right? So you need your base case here, which is if tree is null, then we don't have to do anything. Okay, so that is a perfectly fine recursive traversal. And when you did, regular binary tree traversal, left right node, or whatever, in your programming assignment, right, all you really needed was 4 statements. See if the root's null, and if it is, exit. Otherwise, do your 2 recursive traversals, print out the root data. Okay, but here's what I saw. In some cases, you can go a little crazy with these null checks, right? And it's not wrong, but I'm seeing things like if tree left is not null, then traverse tree left. If tree mid is not null, traverse tree mid. If tree right is not null, traverse tree right. If tree is not null, print tree data. All right? Now that's not wrong. It's going to do the right thing in the end, but you're doing more work than you need to, because recursion is magic. Okay? Recursion will take care of these things for you if you set it up right. So in the beginning of this, I said if tree is null, return. So what's my documentation for my traverse function say? It says something like, you can pass this any binary tree or any 3-way tree you want, including a null one, and it will correctly traverse it. Right? Which means that I don't have to worry about if tree left is null. I can just say traverse tree left, and if it's null, I can be confident this will do the right thing. It'll return right away. I need to check explicitly in the beginning to see if tree itself is null, because I don't want to try to descend into tree's children if tree doesn't have any children. Right? Not if its children are null, but if tree itself does not have a root node. Right? And this is a subtle thing between definitions almost. Right? Here's a tree containing 1 node. I can ask for that node's children safely. Right? Here's a tree containing no nodes. I cannot ask for this node's children, right? Because there is no root node. So this, if tree is null, is picking up this case where your tree actually doesn't even have a root. If it's got a root, you're fine looking at tree left, tree mid, tree right, tree data. So that's just something to keep in mind. And that came up with the happy and funky and sad trees also. So a 3-way tree is happy if it's empty, or if exactly one of its 3 subtrees is happy. So happy trees are silly. Same 3-way structure, left, mid, right. So it's happy if it's empty, or if exactly one of its 3 subtrees is happy. So happy T. So if the tree is empty, it's happy. or if exactly one of its 3 subtrees is happy. So happy left equals happy T left. Happy mid equals happy T mid, and so on. So if its left subtree is happy, this will be 1, otherwise 0. If its mid subtree is happy, that'll be 1, otherwise 0. And if the right is happy, that'll be 1, otherwise 0. So the tree is happy if it's null. We already took care of that. The only other possibility is exactly one of these is 1 and all the others are 0. Okay, so how do you do that? Well, there's a few ways. The most direct way, probably, if happy left equals 1 and happy mid equals 0 and happy right equals 0. Or happy left is 0, happy mid is 1, happy right is 0, or this is 0, this is 0, this is 1, then my tree is happy, return a 1. Otherwise, return a 0.
You said they're returning 1 or 0, right? So couldn't you sum them up?
Or you can just sum them up. And if left plus mid plus right is equal to 1, your tree is happy. So return a 1, otherwise return a 0. And that's a slicker way, and it takes a lot less code, a lot less writing. But something along those lines, something that will tell you if exactly one of these is equal to 1 and the others are equal to 0. And there's a lot of ways that this can get done that don't work. And some of that was just almost like overthinking it, maybe. But I got some like really interesting nested if statements and such. But yeah, so again, same thing that I was seeing before. In some cases, people were successfully calling happy on these subtrees, but just not doing anything with the return value. So you called it, and that call went through some work internally to decide if the tree was happy or not, but you're not doing anything with the result of that. Right, so you got no hope of actually knowing if exactly one subtree was happy. And also, you don't have to check to see if T left is null because you've got this up here. If it's null, it's going to do the right thing. And in this case, if you put in explicit checks for T left being null, right, you got to know what it's supposed to return in that case. And so that's a good one to review and make sure you can do if you had trouble with it. I think that was the bulk of it. Question 4, you were either deleting every other node or you were duplicating the list to create a new node. And that was the question that I promised you was going to be more challenging than the others. But people did a good job with that, so I was really happy. And if you want to talk about that, we can talk about it offline if you want to come in and look at your exam. But I didn't actually see anything in here that caused me concern. And then the other questions were, I don't think we need to go through them. Again, you're welcome to ask questions or come by and look at your exam. But balancing an AVL tree and heapifying or adding things into a heap. Oh yeah, I did want to talk about this though. Just because. So, dynamic programming, right? Implementing a memory cache. And you did this in the knapsack problem, but the knapsack problem was a group problem, so I think some people didn't get as much experience with dynamic programming as others. So here's a bizarre function called cool. It's obviously recursive. If the argument's less than or equal to 3, it returns 5. Otherwise, it calls itself a couple of times and returns that. So this is going to be a big bundle of recursive calls. So we want to speed it up by putting in a memory cache. And we kind of talked through this before the exam. So here's some function that takes an argument and returns a value. So there's this big recursive section, which is very expensive time-wise. It's got all kinds of recursive calls, and this is where all of your performance goes away. So the way that we add memory caching, dynamic programming to this is we put something in the beginning, we put something at the end. Okay, in the beginning we say if save n is valid, just return it. So we have an array of memory values, right? And I tried to make it nice by saying your arguments between 0 and 50. So I could make this, an array of 51 integers, this save array. And how do we know if it's valid? Because if you look at this function, it's always going to return something that is positive, right? Because 5 is positive. So you could just initialize it to 0, or you can make a structure with flags or whatever. But somehow see if this entry has been saved, and if it has, just return it. Okay? Otherwise, do your big, long, expensive thing, right? And the last statement of your old code was return blah. Okay, get rid of that and just say save bracket n equals blah, and then return save bracket n. So the way you add this memory caching is just you add something in the beginning and something at the end. You don't need to change this recursive stuff. Just make sure that at the end, instead of returning your answer, you take your answer, save it in your save array, and then return that answer. And in the beginning, check your save array to see if you've already calculated this value. And again, I saw lots of solutions to this that did work, but you did a lot more coding and thinking than you probably needed to, which is okay in general. But I want to make sure you understand that it's sufficient to, in this case, look up the element corresponding to ha in the very beginning, and if it's saved, return it. Otherwise, save 2 times cool plus 3 times cool in your array and return that at the end. And the thing I was seeing was lots of tinkering with this save array throughout this, calculating this and storing it in the save array, and calculating this and storing it in the save array, and then pulling those out, and so on and so forth. Again, the recursion will handle that for you, right? So the takeaway, I think, is think about what the recursive behavior is, right? Imagine a 1 or 2 sentence description of your recursive function, and everything that it does, and everything that it expects, and everything that it can handle, and then take advantage of that. So if it can handle a null argument, that's fine. Handle a null argument. If your dynamic programming will, take care of efficiently executing this function for any value that you give it, then I don't need to monkey with this and say, well, let's try to speed up my call to cool haha -1, right? I can just call cool haha -1 as long as I've got code in here that speeds this up, right? I don't need to add extra code. Is that making any sense? Okay. All right, and I think that was it. So there's quick sort, insertion sort, selection sort, hashing question, and the try question. Oh yeah, so one comment on hashing. I didn't mean the hashing to be a mathematically hard thing. So let's talk about modulo for a minute. So number modulo divisor equals the remainder of some number divided by a divisor. Okay, it's the stuff that's left over when you divide. So 17 modulo 5 equals the remainder of 17 fifths. Well, 17 fifths is 3 with 2 things left over, right? 5 goes in 3 times, that gets you to 15. You got 2 left over. That's what 17 mod 5 is. Okay, so 2 special cases that you should know. I don't know. 5 modulo 17 is the remainder when you take 5 and you divide by 17. Well, how many times does 17 go into 5? Goes in 0 times, and what's left over? 5. So any time that this is smaller than that, this modulo that is just going to be whatever this is. The other one is when you go modulo 10, right? What do you get if you divide some number by 10? Well, you just shift the decimal point over. And what do you have left over? It's just whatever this digit is. So I did modulo 10 on the hash question to try to make it a little easier for you, but I confused people instead. Sorry. So, and again, you know, if you were to 3 modulo 10, that's still just going to be 3. Either because you say, well, 10 goes in 0 times, and 0 times 10 is 0, and then we have 3 left over to get to 3, or you just take the last digit because it's mod 10, and it's always the units digit you get back. All right, so I have your exams in my office if you want to go over any of that in your particular case. All right, you ready for some Java?
Yeah.
All right. So let's talk about classes and objects for a minute, because everything we do is going to be related to classes and objects. In C, you know, we have functions like main, which is always present. That's the function that is your main program. And it looks like a function. It's got arguments, it's got a return value, it's got curly brackets at the beginning and end, but it's a special function which the operating system knows it should look for and it should execute when you say a.out or PA5 or whatever your executable is called. In Java, everything is a class. It's like a structure. Okay, so structure is in C. A structure is a new type of variable that contains a bunch of fields. So it might have a few integers and a character array and a pointer to a struct node or something, right? A class is like a structure, but it can also contain code. Okay, so it's got fields, variables associated with it, but it's also got executable code associated with it. We don't have to worry about the executable code for a few minutes. We can just think about this as a type of structure, a Java version of the C struct statement. But our main program is part of a different type of class. Okay, so when I create a file such as my main, right, my main.java, I'm actually defining a class called my main. And inside this class is where I'm going to put my main program. Okay, now I can call this class anything I want as long as it matches the name of the file. But inside there I have to have a function called main, which is public static void main, parentheses, string, bracket, bracket, args, close paren, semicolon, right? The usual but it's got to be inside this superstructure, right? This class, because that's how Java is going to know where to find my main program. I'm going to say Java my main. I'm telling it the name of a class. It's going to look in there for a public static void main. We'll come back to that later. You don't need to understand all the details of those mechanics to be able to do this part of Java, to be able to write main programs and deal with classes. So let me pin down some terminology. So we'll talk about classes and objects. A class is like a struct. An object is like a variable. And I don't have perfect definitions for these, but you'll develop your own definitions internally as we work with these things. But first order definition, a class is like a structure. Okay, it's like saying struct node curly bracket, blah blah blah, close curly bracket. Okay, in some sense, it's like a blueprint or a circuit diagram. It's a description of something, but it is not actually the something that it describes. Just like when you say struct T-node, curly bracket, blah, 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 you've described what a T-node is. You haven't actually created a T-node. You have no T-node in your program yet just by saying struct T-node. Okay. When you say struct T-node star root, right, now you've got something pointing to a T-node. Okay, that's what an object is like. So an object is an instance of a class. The class describes an object. The object is the actual thing. Okay, so I could have a rectangle class that says a rectangle is something that has a width and it has a length and it has a color. Okay, it's just a description. By writing that description in my program, I have not created any rectangles. But I can say I want a rectangle named R1, which is an instance of this rectangle class. And now I've got a variable named R1 that represents a rectangle. Okay, so classes and objects will use those terms, and we'll try to be consistent about it. Okay, so this is going to be my main program, but let's make a rectangle class first. So there's a useless comment that says this is a class for a rectangle. So what does a rectangle have? It's got a length. It's got a width. Let's call it a height. And maybe that's all our rectangle has, just a length and a height. Okay, that's a perfectly fine class definition. I can compile that. And it compiled and it gave me this rec.class file. That's the actual bytecode, right? The JVM will understand. So that describes a rectangle. Okay, so in my main program, and the IDEs will write that for you, if you like. Every time you create a class, it'll say, would you like a public static void main? You can just check a box and it'll fill in that line for you. So public static void main, so let's just put some print statements in here. So we'll put a message saying that we're inside the main program. Let's make a rectangle. So I can say rectangle R1, and that's like saying integer I. Integer I says I is an integer. Rectangle R1 says R1 is a rectangle. Right? What's a rectangle? It's this thing. It's a composite type of variable that has a length and a height. So let's just print out R1's length. So we'll just use a print statement, print out R1.length. And guess what? It's not initialized. It's actually saving us from the equivalent of a seg fault here. So it's telling us at line 7, we're saying R1.length, but R1 might not have been initialized. So what's the problem here? When we say rect R1, rect is like a structure. This is like saying, you know, struct rect star R1, right? R1 is referring to a rectangle, but we still haven't actually created a rectangle to which R1 will refer. When we say integer I, we're saying I is going to be an integer, but we haven't given I a value yet. Right? I is supposed to be an integer, but it's got some random value right now, right? Rect R1 has some random value right now. It's not any particular rectangle. In fact, the random value it has is null. So we need to do something like a malloc statement. We need to actually say I want to construct a rectangle. So we say rect R1 equals new rect with parentheses. So this constructs a rectangle, or the old term is instantiates, creates an instance of a rectangle. So is rect a class or an object?
Class.
Rect itself is a class, and R1 is an object. Okay, so it's an instance of the class. Yeah?
So when you do new rect, does that return a pointer to a rectangle?
Effectively, yes. And we never use the word pointer in Java.
So then rect R1, R1's a pointer to a rectangle, not a...
R1 is a pointer to a rectangle when you say rect R1, yeah. It's a reference to a rectangle is the gentler way to say it. But yeah, it's basically a pointer. Which is important because if we say if R1 equals R2, we're comparing pointers. We're saying are they referring to the same object, not do they have the same length and width. Okay, so here I said R1 equals new rect, and we're going to print out R1.length. So I can compile my main, and when I execute it, it tells me R1 has length 0. Well, I never said that the length was 0, but doubles default to a 0 if I don't initialize them. So everybody who likes default values, here's your chance. Well, we could change the default values. So let's start off with a 5 by 7 rectangle. So now if I run this, it tells me R1 has length 5. Not a big surprise. So let's change the length of R1. So I'll say R1.length equals 50, and then I'll print out R1.length. And so R1's length was 5, and then I changed it to 50, and the print statement confirmed that its length was 50. So this is very much like C, right? We're not using arrows, we're just using a good old-fashioned dot to access a field. And R1 is effectively a pointer to a rectangle, so when we say R1 dot, it's kind of like what we used to say R1 arrow, right? We're automatically dereferencing. We're finding what R1 points to, which is a rectangle, and we're accessing the length field. So at this point, you recall 224 and the fact that you know all about Unix, and we're in a Unix environment, and these commands for compiling and executing are a little cumbersome. And since I'm planning to do this a few hundred times, I might set up an alias. I might alias C to be javac star.java, alias R to be, go ahead and execute my main, and now I can compile like that, and I can execute like that. Well, that's going to save me an hour at the end of the day, or maybe at the end of the week. And I could alias V also to be VI, but I'm only editing a few files. All right, so that's enough to start working with objects and classes, right? Well, one thing that we're going to talk about a lot, or one thing we're going to use a lot, is this idea of information hiding. The fact that I have a double named length and a double named height inside my rectangle makes it very tempting for my main program to say, hey, I want to change my length to 50. I'll just say r1.length equals 50. Well, imagine the world in terms of producers and consumers. So I am the person who wrote this mind-numbingly fabulous rectangle package, right? And I'm going to sell this to somebody who wants to work with rectangles. And so they gave me, a penny, and I gave them my rectangle package, and now they can do this kind of stuff, right? Well, maybe I'm doing something weird inside my package with the length. Maybe I'm converting it to millimeters for some reason. Maybe I've told them that that they can do certain things with this, and then I changed my mind on what length was going to represent. And for various reasons that'll be more obvious later, I may not want them to be able to do something like this, set r length equal to 50, or even access r1.length. Because maybe my intention is internally I'm going to store length in some other weird way, and I'm going to give them access to it in a controlled way, but I don't want them to directly come in and see these things, right? This is like the stack pointer when we implement a stack. Does the stack pointer start at 0 or -1 or 100? That's my business, right, as the producer of this code. That's not the concern of whoever is consuming this code. So I can actually say these things are private. And if I do that, and I try to compile my code, my main program will get an error saying you don't have access to that field. So I can actually hide pieces of my structure, my class, from whoever's using it. Now they can still create a rectangle, but they can't come in and look at or change these private fields. And that's going to be really useful because it lets us do all kinds of things and set things up one way and then change it to another way and be guaranteed that it's not going to affect the user's code. Because we're going to provide them a way to get to these variables and to modify these variables, which is going to be very controlled. So we're going to create what are called accessors and mutators. All right, so we'll start with those tomorrow. I'll throw this code up on the server for that link under